Sorry about that. If you're, hopefully you're coming from 2-3 part one. This is 2-3 part two. We were right in the middle of this problem about rational functions with asymptotes. Basically, we were trying to figure out where the horizontal asymptote was for this one as x gets really, really big, absolute value of x gets really, really big. So I put 10 in for x, and we got 1 1/3. And now I'm saying, well, what if we put 100 in? Then we get 302 over 204, which ends up being 1.48 about. If I put 1,000 in, I get 3,002 over 2004, which is close to 1.5. It's like 1.49. If I put 1,000,000 in, I get 1.449. Okay, like we get closer and closer, but we never will hit 1.5. So my horizontal asymptote is 1.5. Y equals 1.5. Okay. And on the other side, if I put negatives in, I end up, if I put something less than -2, I mean, my vertical asymptote was at x equals -2. And now I'm going to put -3 and -4 in and see what happens. And I get a curve right here. Once you have your vertical and horizontal asymptote, you know that your graph, your rational function, is going to kind of hug those asymptotes. Okay, so rational functions are a little tougher to deal with because they have these horizontal and vertical asymptotes. Okay. So here's a place in business, for you guys that are business majors, which all of you are. The rational functions are often used to model cost benefit, okay, because they rise quickly as they approach some certain number. For example, here's a cost benefit model. Y equals 18x over 106 minus x, where y is the cost in thousands of dollars of removing a certain percent of a certain pollutant. The domain of x is a set of all numbers from 0 to 100, okay? 0% to 100% of this pollutant is being removed, okay? So we put in some numbers and see what we get, okay? Put in 100% for x, see what you get, okay? Put in 100, put in 95%, 90%, 80%, and you just start getting an idea of what happens with this rational function. To save time, I have it graphed for you. Okay, when I put 100 in, I got 300. It's plotted that point. 95 was 155, 90 was 101, 80 was 55. Okay. Notice what my vertical asymptote was, 106. And if you look back at the function, it makes sense. Okay, because 106 minus 106 would give you 0 in the denominator. Okay. So that's where, sometimes we can have an idea of how, how this is working. The closer and closer to 100% that we get, the bigger, or the closer and closer to x being 106, the bigger we get. Okay, but it never is going to actually touch that asymptote. Another place that we use a rational function in business is when we take the average cost. We already learned that the marginal cost function is mx plus b. M is the marginal cost, b is the fixed cost. The average cost would be then taking that cost function and dividing by the number of units. Just like any average, you divide by the total number. Okay, this is a rational function. It has a vertical asymptote right at x equals 0. X can't be 0, and a horizontal asymptote becomes y equals m. Okay. The vertical asymptote reflects the fact that as the number of items produced approaches 0, then the average cost per item becomes huge, okay? Because the fixed costs are spread over fewer and fewer items. The horizontal asymptote shows that as the number of items becomes large, the fixed costs are spread over more and more items. So most of the average cost per items is the marginal cost. Okay, so in other words, these are just examples of where these are used. Okay, so we're going to move forward into section 2.4, which is a new type of function called the exponential function. It's where the exponent is the variable x. Okay, f of x equals some number to the x power, as long as a is bigger than 0 and not equal to 1. You can think about why it wouldn't be have the same properties as every exponential function if a was 1. Think of what 1 squared, 1 cubed, 1 to the 4th, 1 to the 5th. It's always going to be 1. It's just doesn't have all the other properties of a number greater than 0. So if I'm going to graph y equals 2 to the x, just to get an idea what that looks like. I'll start with 0. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. Okay, so I'm at 0, 1. 1 gives me 2. 2 gives me 4. 3 gives me 8. You see this curve? It's just going to get bigger and bigger and bigger. But then what's happening with negative values of x? Okay, thinking back to what a negative exponent does. 2 to the negative 1 means 1 over 2 to the first. 2 to the negative 2 means 1 over 2 squared. 2 to the negative 3 is 1 over 2 cubed. So we end up getting negative 1 gives me a half, negative negative 1 gives me a half, negative 2 gives me a fourth, negative 3 gives me an eighth. I'm going to be really close to 0, but I'm never actually going to be 0. We do have a horizontal asymptote here at y equals 0. Okay, because I'm always going to have 1 over 2 to the something. It might be 1 over 2 billionths, but that's still not 0. It's really, really small, but it's not 0. This is what your exponential functions look like in general. They start out real slow, but then the bigger x gets, wow, does it take off. That's why they say a lot of times, oh my goodness, it's growing exponentially, and that means really fast. Okay, and that's why. So the graph of y equals 2 to the negative x. Okay, so we still have 2, just like we did up here, but we're raising it to the opposite of x. So 0 is still going to be 1. Okay, 2 to the negative 0 is still 1. But if I put 1 in for x, 2 to the negative 1 is a half. So 1 gives me a half. If I put 2 in, that's 2 to the negative 2, which is a fourth. If I put negative 1 in, that's 2 to the negative negative 1. That's 2 to the first, or 2. Then if I put negative 2 in, oops, that goes there. That's 4. Okay, so we end up getting our graph. It's a decreasing function. Okay, it has the same horizontal asymptote, but instead of getting bigger as x gets bigger, it gets smaller as x gets bigger because we're taking the opposite of x. So just be careful. An exponential function, sometimes it's growing real fast as long as x is positive. But if you have 2 to the negative x or 3 to the negative x, then it's a decreasing function. Okay. All right. Wait, let me just make sure. Yeah. Okay. So let's just play with graphing an exponential function if we have something like negative, or the opposite of 2 to the x plus 3. Notice this is read the opposite of 2 to the x. I'm not taking, this isn't negative 2 to the x. That's a whole different, no, that is not what we're doing here. Okay, we're not doing that. A is 2, and then I'll take 2 to the x first, and then I'll apply the opposite. Okay, so let's see what happens here. I'll put 0 in. 2 to the 0 is 1. The opposite of 1 is negative 1. Negative 1 plus 3 is 2. Let's put 1 in. 2 to the 1 is 2. Opposite of that is negative 2. Plus 3 is 1. Let's put 2 in. 2 squared is 4. The opposite of 4 is negative 4. Plus 3 is negative 1. Let's put 3 in. 2 cubed is 8. Negative 8 plus 3 is negative 5. Okay? All right, I'm seeing what's happening there. Let's go the other way. If I put negative 1 in, I have 2 to the negative 1 is a half. Negative a half plus 3 is 2.5. If I put negative 2 in, I have negative a fourth plus 3, which is 2 3/4. I start seeing that my horizontal asymptote is y equals 3. And the negative in front kind of flip my graph over. Okay, I'm used to a, 2 to the x, like we saw on the previous page, goes like so. But putting the negative here in front flipped it upside down and made it go like this. Okay, and it also, the plus 3, instead of having my horizontal asymptote at y equals 0, I'm up at y equals 3. Okay, so this is the graph of y equals the opposite of 2 to the x plus 3. And again, you're welcome to use your graphing calculator to see that instead of doing it by hand. Solving exponential equations, you have the option of, before we get into logarithms, where we'll learn another method to solve these. Right now, we're going to rewrite them using the same base. Okay, I can write 9 as 3 squared. So I have 3 squared to the x equals 3 cubed. I can write 9 as 3 squared. I can write 27 as 3 cubed. When I have a power to a power, remember properties of exponents says I multiply those exponents together, right? If I have x squared cubed, most of you would know that that's x to the 6th. You multiply the exponents. So here I can write this as 3 to the 2x equals 3 cubed. Well, once I rewrite using the same bases and I use these properties of exponents, that's what I just did here, 2 times x is 2x. Now I can set the exponents equal. 3 to this power is only going to equal 3 to this power if the powers are equal to each other. So I'm going to set my exponents equal to each other. Okay, so x is 3 halves. That's my answer. That 9 to the 3 halves equals 27. Okay, we can check that on our calculator if we want, or I can just think in my head, let me see, 9 to the 3 halves. The denominator, remember, is the root. So that means square root of 9 cubed. Well, the square root of 9 is 3. 3 cubed, yep, that's 27. So yes, 9 to the 3 halves is 27. Okay, that's how you solve those problems. Whoops, I think I missed one, didn't I? You guys have your notes. I was going to do this one as well, okay? Sometimes they're, again, I have to get them in the same base. 32 I can write as 2 to the 5th. So I have 2 to the 5th to the 2x minus 1. 128 is 2 to the 7th. I have 2 to the 7th to the x minus 3. I'm going to use the properties of exponents and multiply my exponents together. So that's 2 to the 10x minus 5. And this is 2 to the 7x plus 21. When I multiply, I have to distribute my 7 through. Now that I have my bases the same, raised to 2 different exponents, I just have to set my exponents equal to each other. Okay, so I'm going to say, when does 10x minus 5 equal 7x minus 21? Well, I'll subtract 7x. I'll add 5 to the other side. No, that's not minus, that's plus. So 3x equals what, 26? So it looks like my answer is 26 thirds, or you could write it as 8 2/3, however you want. Okay, that's the answer. That's solving exponential equations. Okay, so please come back for 2-4 part 2.